Welcome back, students, to our explainer on Advanced SQL. I'm absolutely thrilled to guide you through this material today. Think back to our last lecture on Chapter 7. We focused entirely on asking questions of our database using the select statement, right? We were basically data detectives. Well, today, in Chapter 8, our role fundamentally changes. We are stepping up to become the architects. We're going to learn exactly how to build the database structure from scratch and actively change the data within it. This is a crucial step in your software engineering program, so let's get right into it.
Okay, let's take a quick look at our roadmap. We'll start with an introduction to Advanced SQL, move into creating tables and constraints, then cover data manipulation commands, followed by transaction control commands, dive into procedural SQL and automation, and we'll wrap up with a final summary and review.
Section 1. Introduction to Advanced SQL, Shifting Paradigms.
So we're transitioning from simply querying existing data to actively building structures and altering information. This really brilliantly illustrates the shift. On the left, we have what we learned previously, passively asking questions. On the right, we have our new tools, Data Definition Language, or DDL, and Data Manipulation Language, or DML. You can kind of think of DDL as pouring the concrete foundation and framing the walls of a house, while DML is moving the furniture in, painting the walls, or, throwing the old furniture out. Both of these are absolutely essential for a functioning dynamic database.
Section 2. Creating tables and constraints, laying the foundation.
This is where we act as true architects. We begin with the create table command. This is a fundamental data definition language command. Before you can store a single piece of data, you absolutely must use this command to create the blueprint that defines exactly where and how your data will live. You're going to specify the table name, the column names, and the specific data types for each column, basically telling the database whether a column is going to hold text, dates, or numbers. But simply creating columns isn't enough, is it? We have to enforce rules to keep our data accurate and reliable. The crucial point here is that constraints must be defined directly in the SQL code. Let's walk through these. The primary key constraint strictly enforces entity integrity, meaning every single row has a unique identifier. The foreign key constraint enforces referential integrity, ensuring relationships between your tables are valid. Not null prevents a user from leaving a mandatory field empty. Unique prevents duplicate values in a column that isn't a primary key. And finally, check validates specific conditions, like say making sure a product's price is always greater than 0.
Now there is a strict and honestly fascinating rule for creating related tables. In a database, we often have one-to-many relationships. For example, one vendor can supply many products. The strict rule is this: you must build the parent table, the one side, like vendor, before you build the child table, the many side, like product. Why? Well, because the child table contains a foreign key pointing to the parent. You literally cannot point to a table that doesn't exist yet. Prioritize doing this in the correct order, and you will completely prevent orphan data and structural errors.
And while we're discussing foreign keys, we absolutely have to talk about the onUpdate cascade and onDelete cascade clauses. Imagine a vendor's ID code changes. If you just change it in the vendor table, all the linked products in the product table are suddenly pointing to an old, non-existent ID. To minimize these errors, the onUpdate cascade clause tells the database, hey, if the parent record changes, automatically flow that change down and update all related child records. Similarly, the onDelete cascade clause ensures that if a parent record is removed, all of its orphaned child records are safely deleted as well. It's just a fantastic way to maintain perfect referential integrity automatically.
Section 3. Data Manipulation Commands, Moving Inventory. Okay, quick recap. We've successfully built our tables and locked them down with strict constraints. Now it's time to actually add data using the Insert Into command. And just like when we were building tables, the order matters tremendously. When inserting data into a one-to-many relationship, you must insert the parent row, the one side, before you insert the child row, the many side. If you try to insert a new product for a vendor that you haven't added to the database yet, the system is going to throw a catastrophic foreign key error and flat out reject your data.
Once your data's in, you will inevitably need to change it at some point using the update command. But I need you to listen very carefully to this warning. It's a common trap for students. Always use a where clause with the update command. The where clause tells the database exactly which specific row to modify. If you issue an update command without a where clause, the database assumes you mean everything, and you will accidentally overwrite every single row in the entire table with the same value. It is a very quick way to ruin your company's database and make your boss very, very unhappy.
Section 4.
transaction control commands, the safety net.
So if you happen to make a terrible mistake like that update without a where clause, you desperately need a safety net. Think of these transaction control commands as your absolute best friends in database management. In many database systems, when you insert, update, or delete data, the changes aren't instantly permanent. They're held in the temporary state. Commit acts as the database's ultimate save button. Typing commit takes those temporary changes and permanently writes them to the database. On the other hand, rollback is your undo button. If you realize you just ruined your table with a bad update command, typing rollback will immediately undo all changes since the last commit, restoring the database to its previous consistent state.
Section 5. Procedural SQL and Automation. Smart Database Logic.
All right, let's recap where we are. We've built the structure, we've moved the data, and we know how to save or undo our changes. But a modern database is more than just a dumb storage locker. Standard SQL is purely a query language. It's declarative. You tell it what you want, but it doesn't have the ability to make dynamic decisions. It can't loop, and it can't process if-then logic. Procedural SQL, like Oracle's PL/SQL or Microsoft's Transact SQL, fixes this. It adds traditional programming features so you can actually run complex business logic directly on the database server itself, rather than relying entirely on a separate software application.
Procedural SQL allows us to create two incredibly powerful tools: triggers and stored procedures. Think of a trigger as an automatic security camera. It's a block of code that runs automatically in reaction to an event, specifically an insert, update, or delete. For example, if an item is sold, causing an update to your inventory count, a trigger can automatically check if the new quantity has dropped below your minimum threshold. If it has, the trigger automatically flips a reorder flag. No human intervention needed. Now, a stored procedure, on the other hand, is a manual master switch. It's a named collection of SQL statements saved directly on the server, but it must be manually called by an application. This is incredibly efficient. An application just sends the name of the procedure over the network, rather than sending hundreds of lines of SQL code, which dramatically minimizes network traffic.
To make procedural SQL work effectively, we must also recognize the cursor. Standard SQL is set-oriented. It returns a whole set of rows at once. But programming logic usually processes things one record at a time. The cursor is a reserved memory area that temporarily holds the query output, allowing your procedural code to loop through the results row by row. It beautifully bridges the gap between set-oriented SQL and record-oriented processing.
Section 6. Final Summary and Review. The Final Exam Prep.
We've covered a lot of ground today, transitioning from just asking questions to actually building and automating. I strongly advise you to memorize this summary for your exams. Prioritize understanding the DDL order. You must always create the parent table before the child table. Remember the extreme danger of the DML update command. Literally never forget your where clause. Know that commit permanently saves your transactions, while rollback acts as your emergency undo. And finally, understand the distinct behavior differences in procedural SQL. Triggers react automatically to data changes, whereas stored procedures sit quietly until they are manually called.
Before we wrap up this explainer, I want to leave you with a final thought to ponder. We've talked all about manipulating data and using commit to save it. But what if 100 users are all buying products and updating the inventory at the exact same millisecond? How does the database prevent lost updates and complete chaos? Consider this scenario carefully, because it perfectly tees up our next crucial topic in software engineering: transaction management and concurrency control. Thank you so much for joining me today, and I will see you all in the next lecture.